Ladies and gentlemen, please welcome Corey Inkpen, Research Manager and Principal Researcher, Microsoft Research.
Good morning. I hope you enjoyed last night. Welcome to the second day of the Microsoft Research Faculty Summit. Today promises to be just as exciting as it was yesterday. To start the day, it is my pleasure to introduce Dr. Amy Greenwald, who is an Associate Professor of Computer Science from Brown University. Amy also spent time as a visiting researcher at Microsoft Research New York. Amy has been widely recognized for her work, and she was named a Fulbright Scholar and was awarded a Sloan Research Fellowship. In 2002, Amy was nominated for the Presidential Early Career Award for Scientists and Engineers and was named one of CRA's Digital Government Fellows. Please join me in welcoming Amy.
Thank you, Corey. Good morning, everyone.
Morning.
Thank you for waking up to be here. Or perhaps like me, you're on East Coast time and you were awake anyway. If you came to hear about deep learning, I'm sorry to disappoint. I have nothing beyond that to say about deep learning. Well, it's always a pleasure to be here in Redmond. I was on leave, as Corey mentioned, visiting Microsoft in New York, but was here for Tech Fest a couple of years ago. And in fact, one of the results I'll talk about, we discovered, I think, just outside this room during a coffee break. So my research is primarily concerned with multi-agent systems, in the sense that I study systems where multiple agents, both AI and human, interact with one another. And in general, these agents are assumed to be strategic. So this means that they're endowed with some objectives, and they act so as to achieve those objectives. So this is the exact same behavioral model that underlies much of game theory. So computer scientists like myself often borrow ideas from game theory to apply to our multi-agent system research. And likewise, we sometimes make contributions to game theory. And in fact, during today's talk, I will talk about one such contribution. And let me warn you that that part of the talk is a bit technical. I hope everyone has their coffee. So, and then during the second half, I'll transition to talking about kind of straight up AI. So, as you are no doubt aware, there have been tremendous advances in recent years in applying AI to social good, in healthcare and education, et cetera. And likewise, there have been advances in applying an area of game theory called mechanism design to social good, in healthcare, in education, et cetera. So I'm going to start today by telling you about some of these successful deployments. And then I'll transition to talking about some of the remaining challenges and give some suggestions as to how we might tackle them. So what is this mechanism design? So well, for starters, what's a mechanism? A mechanism is a game in the game theoretic sense. And that means that it's rules by which some outcome will be determined after the participating strategic agents take action. But particular to mechanism design is the idea that each agent has access to some private information, and that their action in the mechanism is going to involve reporting some function of that private information to the center, who is the entity implementing the mechanism. So for example, plurality voting for determining the outcome of an election is a mechanism. And in an election, the agent's private information is maybe their ranking of all the candidates. And then their action might be, for example, to report their most preferred candidate. And then in plurality voting in particular, the winner is declared as the candidate who receives the most votes. So the mechanism design problem then is to design a good mechanism in some sense. So in the case of voting, a good mechanism would be one who elects a candidate who is preferred by the voters in aggregate. Our electoral college has come under some serious criticism this century for electing presidents who are not preferred by the majority of voters. So some would say that that is not a good mechanism design. Another desirable property of mechanisms is that they elicit truth-telling behavior. So if, for example, you're a supporter of Bernie Sanders, you should not be incentivized to vote for Hillary Clinton. You should be free to vote your conscience. If a mechanism is not truth-telling, then it can't be expected to be a good mechanism because it can't determine an outcome that reflects the participating agent's preferences if it doesn't know those preferences. So in short, a mechanism is a set of rules for determining an outcome based on reports by the participating agents about their private information. And then the mechanism design problem is to design a mechanism that achieves some goal. And doing so usually requires truth-telling or something close to it because a good outcome can't be generated by false reports. So like the old adage says, garbage in, garbage out. So as our first example of the successful deployment of a mechanism, let's discuss kidney exchanges. So currently there are roughly 100,000 people queued up for kidney transplants in the United States. And kidneys, like other organs, are donated by the deceased. But interestingly, they can also be donated by the living, because people can live with just one kidney. And indeed, it's quite common for family members to volunteer a kidney to save a loved one. The trouble is, not all kidneys are compatible. And to complicate matters more, some kidneys are more compatible than others. So it could well happen that I need a kidney, and say my husband's kidney, he's going to donate for me, is not particularly compatible with me. But maybe Corey's partner also needs a kidney, and Corey's kidney is not compatible with her. But perhaps Corey's kidney is compatible with me, and my husband's with her partner's. So under these circumstances, a trade can be arranged, like you see here. And indeed, there can be 3-, 4-way, et cetera trades. So facilitating these trades is the goal of kidney exchanges. So how is this a mechanism design problem? Well, the organizers of the exchange will announce some rules by which matches will be made. And the goal, then, is to match as many kidneys to patients as possible. Truth-telling, welfare maximizing, so making the most matches, mechanisms do exist for certain variants of this problem, like when donor-recipient pairs will report their preferences to the center directly. But in most implementations, hospitals are the ones that do the reporting. And hospitals might decide to do their own internal matching first, and then report just kind of the leftover pairs to the center. And those can be harder to match. So you can see that truth-telling is maybe not quite there, and so as a result, you may not get the optimal trades, the most trades you could possibly get in that setting. But still, kidney exchanges are up and running and facilitating many trades and saving many lives. A second example of the use of mechanism design in practice is in the realm of school choice. So for those of you who don't have school-aged children, I do. School choice is an attempt to allocate students to public schools according to the students', or perhaps more accurately, the parents' preferences over schools, rather than allocating them in the traditional way, which was just by neighborhood, which can sometimes leave children who live in neighborhoods with underfunded schools with less than ideal options. So in a typical school choice implementation, parents submit to the district a list of their top K schools in order. And likewise, the schools will rank students. So they'll rank them, for example, by who lives in their walk zone, or they might rank them by siblings having priority, things like this. So then a matching algorithm processes all these rankings and assigns students to schools, much like how residents are assigned to hospitals. So these problems are instances of the heterosexual stable marriage problem, where the goal is to discover a matching of men to women, such that there are not two matched pairs, so we can imagine two matched pairs, for which a swap would be preferable for some of the people in the matching. Because if there were such a swap, the matching would be unstable because that pair would run off and elope. So as in the case of kidney exchanges, truth-telling welfare mechanisms do exist for this setting. But in practice, speaking as a parent, the implementation of school choice in Providence, in particular, has had an unfortunate effect. In particular, it's led to a kind of breakdown of community. So the problem is that we report only this short ordinal ranking of schools, but there's no language to report how important it is for us to actually have our children attending the same schools as our neighbors. So this may seem reasonable because school choice, of course, was designed to give students an opportunity to escape their neighborhoods. But in Providence, at least, school choice is having the effect of cutting up neighborhoods, and it seems it could potentially harm the students more than it's helping, at least some of them. And of course, there's the added problems with the busing costs that are extreme because of the school choice and the time. You know, kids will be picked up at 6:30 in the morning for a school that starts at 8 o'clock. So the time they waste on the bus. But I'm not going to go off on a political commentary here. I just wanted to remark on the dimensionality of the preference reports. So just like in voting, you might have complicated preferences over all the candidates. You can report only one in certain mechanisms. In school choice, likewise, we might have complicated preferences over the schools and the combinations of students that are attending the schools, but we can report only that short list. So, and as always in mechanism design, the extent to which an outcome is good can only be as good as its inputs. Okay, I now want to move on to a third application of mechanism design, which is optimal auction design. And I'm going to go into a bit more detail here, as I'm going to need this to explain some of the results later on. So here's the framework for optimal auction design. So first of all, we'll start with an auction. So an auction is announced for some goods, and bidders are going to report their preferences to pay for the goods. And so this is a mechanism design problem again, because the bidders have some private information about their values for the goods. The bidders also have utilities, and these utilities are the difference between the value of what will be allocated to them and what they pay. And now the auction designer's goal, at least in the so-called optimal auction design problem, the goal is to maximize the total payment. So there are other objectives that you could consider, for example, maximizing welfare, but the optimal auction is the one that maximizes. Optimal is used to mean the one that maximizes payments. And this makes sense, for example, if you're Microsoft and you're running advertising auctions, you want to maximize your revenue. Okay, so as I said, we're going to do this a little more formally because I'll need this for some of my results. So more formally, we have N agents, and they all have private values. These private values are drawn IID from some distribution. And then the bidders are going to use some strategy, denoted here S sub I. And that strategy is a function of their private information. So that strategy is going to determine their bids. So then the auctioneer will collect this B, which is supposed to be bold. I hope you can see that that's bold. That's a vector of bids, one per agent. And so then the auction designer has to design the auction. So what does an auction consist of? An auction consists of two things. It consists of an X and a P. And X is the allocation rule. So that is how we're going to determine who the winner is of the goods. Or in this case, actually, we're just doing a single good. So who's going to win the good? And P is the payment, so that's going to determine what they're going to pay for their winnings. So X and P are the main variables that we have to design in designing our auction. So as we said, the utilities are going to be depending on what you win and how much you pay. So in particular, they're assumed to be linear here. And so it's the value that you have, that's your private value for the good, times your allocation. So you can imagine the allocation X being, maybe it's an indivisible good and you're kind of allocated or you're not. It could be a 0-1 thing. Or maybe it's a probability of being allocated. So maybe it's in the range of 0-1. So this is your positive term for your value times what you're allocated minus what you have to pay for whatever, for participating in the auction. Okay, so that's the model, and then kind of the standard equilibrium concept for this model is called a Bayes-Nash equilibrium. Probably many of you have heard of Nash equilibrium. Bayes-Nash is just, it's Bayesian because we have uncertainty here in that the private values are not known. They're drawn from a distribution. So Bayes-Nash equilibrium is like Nash equilibrium, only we're taking expectations everywhere. So just to remind you what Nash equilibrium is, Nash equilibrium, everybody's best responding to one another. So that means that all the players are utility maximizing, given what everybody else is doing. So Bayes-Nash, same thing, but in expectation. All right, so here is the optimization problem stated slightly more formally. Again, to design an auction, you have to choose an X and a P, so that's what our decision variables are here. Our objective is to maximize our expected payments, as I mentioned, and then we have a bunch of constraints. So let's start with the last constraint. Last constraint, ex post feasibility. This means that we can't allocate more than we have. Okay, that makes sense. We also have an individual rationality constraint. This says that everybody's utilities in expectation, that's what interim means, will be non-negative. Okay, so everybody will be willing to participate voluntarily. And the last constraint is the one that has to do with truth-telling, which we said was one of the features we're looking for in mechanisms. And so we want to make sure that telling the truth is, in fact, utility maximizing. And these top two constraints are basically defining what it means to be in Bayes-Nash equilibrium. So what we want here, these payments, you'll notice, they depend on the bids, which were equal to this S of V thing. So this is S of V is there to denote that everybody is playing an equilibrium strategy. All right, so again, we're looking for auction rules here, so that's X and P, such that in that auction, when everybody is playing equilibrium, so we're anticipating the behavior of the agents, when everybody is playing their equilibrium strategy, that the payments in total are maximized. All right, that's the problem. It wasn't that easy to explain. It's a hard problem to solve. But Myerson solved it in a very elegant way, which I'll show you on the next slide. But basically, the gist of it is that he introduced what's called a reserve price. So a reserve price is going to be some price below which you are not willing to sell the good. So the good, you might think, well, I'll just, it's not worth anything to me. I'll sell it for whatever. But what Myerson showed is that if you choose an appropriate reserve price, that's what you need to do in order to solve this problem optimally. So how did he do that? He did that with that very ugly theorem that I apologize for not having a picture of. If you want me to explain this, I don't have time now, but I'm happy to do it in the halls afterwards. But let me just tell you, what he's done here is that he's fully characterized Bayes-Nash equilibria in this problem. And so how has he done it? He's done it with these two properties. The first property says that the allocation rule has to be monotonic in your valuation. This makes a lot of sense. The higher the valuation, the higher the likelihood that you're going to be allocated. Okay, so monotonicity in valuations is the first property. And then the second property says once you have that, the payments are given by this ugly formula. So the payments are entirely specified by that formula on the slide. So once you've stated what your allocation rule is, you know for sure that these are the only payments that are going to give you the Bayes-Nash equilibrium solution. They have to be these payments. Okay, so that was sort of his brilliant insight. And falling out of this is something called the revenue equivalence theorem. So the revenue equivalence theorem says that once you settle on an allocation rule, all your auctions are going to yield the same revenue. So why is that? It's exactly because of this. Because here you see this X hat here? The X hat shows up in this payments identity formula. And so it has to be, once you pick your X hat, these have to be the payments. So why is this interesting? Think about the auctions that you may have heard of in passing. First price, second price, and so on. So how do these work? So a first price auction is the kind of auction that, when you're going to buy a house. You're going to bid on a house, and you're looking at the house, and you love this house, and it's worth $250,000 to you, you think. But of course, you want to pay less than what it's worth to you. So you think about, how should I shade my bid? I don't want to bid the full thing, because I have to pay whatever I bid. So maybe you bid $200,000 for the house instead, and if you're lucky, you win it. You walk away with that utility of $50,000. So that's a first price auction where you pay what you bid. An alternative is a second price auction. In a second price auction, you pay not what you bid, but you win if you have the highest bid, but you pay the second highest price. This is a lot like what you see on eBay. In eBay, when you're bidding, you have that proxy agent who's bidding for you, and they'll bid up to epsilon above what the second highest bidder is. So that's basically a second price auction, what's being run on eBay. So what this theorem is telling us is that first price auctions, second price auctions, they have the same allocation rule. They always allocate to the highest bidder. And since they have the same allocation rule, they're actually going to yield the same revenue. And so that's true of first price, second price, third price, and so on, and even of what are called all-pay auctions. And in all-pay auction, everybody has to pay, even if you don't win. They all get the same revenue. OK, that was your crash course on auction design. So far, what I've talked about is lots of Nobel laureate-worthy research. So I should mention that the ideas of school choice were introduced by Milton Friedman and really advocated and pushed forward by Al Roth. These are all Nobel laureate economists. Also, Gale and Shapley were involved. I think Gale died before he could earn the Nobel Prize, but I'll mention that he did that work while he was at Brown. And this most recent theorem, this Myerson story with the optimal auction design, he also just recently won a Nobel Prize for that work as well. So that was all the super interesting stuff that was Nobel laureate. Now comes my stuff. OK, we'll see how that goes. All right. So I went into all that detail on optimal auctions because it's very related to optimal contest design, which is something I want to talk to you about. So contests are commonly used to spur innovation. So you might have heard or learned in your readings that the British Parliament passed something called the Longitude Act in 1714 and offered some serious prize money to anyone who could devise a method of precisely determining a ship's longitude while out at sea. And another example of a prize that would spur innovation is the Wolfskill Prize, which was introduced by Paul Wolfskill. Apparently, the story goes, apocryphal perhaps, that he had planned a suicide, but somehow stayed up all night trying to prove Fermat's last theorem and sort of maybe missed the hour of his planned suicide. So when the next morning he rewrote his will offering 100, I can't, how much does it say? It doesn't say, sorry. Does anyone know 100,000 pounds? No, not in pounds. Yeah, 100,000 Deutschmarks, right, for anyone who could prove Fermat's last theorem, which was awarded, of course, in 1997. And there's the Loebner Prize, which is for anyone who can pass the Turing test. OK. Oh, sorry. All right. And so what is the optimal contest design problem? Well, it was stated by Galton, actually, in 1900, or at least some variant of it. So here is how he described the problem. A certain sum, say 100 pounds, is available for 2 prizes to be awarded at a forthcoming competition. The larger one for the first of the competitors, and the smaller for the second. How should the 100 pounds be most suitably divided between the two? What ratio should a first prize bear to a second, and does it depend on the number of competitors? OK, so this is an optimal contest design problem, but you could think of as an optimal mechanism design. So let's look at this problem, and we'll try to, as I explain it, you can try to relate it back to what I said about auctions. So a contest with some rewards is announced. This is like an auction is announced. So competitors are going to make a choice about the degree of effort they wish to expend to produce their contest entry. So this is like the bids that the bidders are going to submit in the auction. The competitors' abilities are going to be their private information. So they have some skill, they have some talent, and maybe the person running the contest doesn't know what that is. That's private to them. And so these abilities, though, are then going to encode a mapping from their effort, how much effort they put in, to the quality of their submission. And then they'll get some utilities. The utilities depend on the rewards they win and the effort expended. And then their goal, of course, is to design a contest that's going to kind of elicit the greatest contribution, so the maximum effort from all of the participants. So that is the contest designer's goal. So one way to think of this, as I mentioned already, we want to relate this to auctions, but in particular, we're going to relate this to all-pay auctions. So in an all-pay auction, as I mentioned, everybody has to pay. So what's an example of a contest that we've all participated in? we've all participated in NSF grant writing contests, right? So in these contests, we all pay. I know I pay a lot dearly every time, right? So we put in all of this effort to write our grants. We have to pay, and we may or may not be rewarded. So that's how you can think of a contest as an all-pay auction. And here we have the model, which is, again, very similar to the model that we saw before. So we have a bunch of agents, and they have their private skill levels. And here's just one difference between what we saw before and what we have now. So we have this effort they're going to invest, and we're explaining the contribution, which is going to be this quality of their submission that's describing their contribution, as a function of their private skill level, which is the V, times the effort that they choose to expend. Okay? So that is everybody's effort. And then because it's all pay, so the X again denotes rewards, E denotes your effort. Because it's all pay, everybody's paying. So everybody will get their rewards maybe, and they are going to be charged for the effort that they expend. Okay, so this connection here, well, actually, the stuff on the next slide was noted by Chalwa, Hartland, and Sivan. So in particular, what they noted was that we can think of that all-pay auction, which is kind of like a reverse auction. We're sort of eliciting submissions here. We're going to pick one of these. You can think of that also as a forward usual auction, just by multiplying the utilities by the private values. So if we do a little algebra here, we take the utilities, which were xi minus ei, and we multiply them by v's. What we can see is that we recover our kind of usual utility function, the utility function I had maybe 5 slides ago for auctions, which was that we were going to achieve our v, our value, times our allocation minus our payment. And here our payment is a Q instead of a P, because we're paying in the quality of the submission that we submit. So what's the point? The point now is that we've converted our contest, which was an all-pay auction, into a forward auction here, and then we can solve it in the usual way that Myerson has solved the optimal auction. So we solve as an optimal auction, and in this forward auction, here's how this works. But in short, we'll set some optimal reserve, and we will have a solution in Bayes-Nash equilibrium with a formula that looks a lot like the formula from the payments identity before. It's been modified slightly to accommodate reserve prices. Okay, so that problem was solved. So we were thinking about that problem, but noticing that the way people work often, you may have heard of this, often follows this so-called 80-20 rule. So the 80-20 rule says that in 20% of our effort, for 20% of our effort, we can produce 80% of our results. So in other words, more and more, once we've done that 20%, whatever we're doing beyond that, it becomes much harder to achieve any further results. So we have increasing marginal costs in this model. So we went back to that contest design thinking about this 80-20 rule as the model of our effort. So the way this works is basically the way we had it before, except that now we have this C function, which you can think of either as increasing marginal cost, as I just described, some convex function like that, or as kind of diminishing marginal returns on your effort. So that's the inverse of the function, right? So we have the more effort you are contributing, your returns are not increasing. They're increasing by less and less. All right, so we are going to solve, or attempt to solve, this same problem that we just saw how it was solved, but this time with these concave or convex costs, whichever way you look at it. All right, so we're going to do the same thing that we did before, which is multiply our values, these private values times the utilities. And so we recover this thing, which kind of looks like what we had before, but it has this annoying C hanging around. All right, so first of all, how are we going to solve this? Well, we need to know what the optimal auction is. Unfortunately, we don't know what the optimal auction is. And even after working on the problem for a year or two, we still don't know what the optimal auction is. But maybe someone here can solve for this optimal auction. So in the meantime, we're going to do the best we can, doing something similar to what we saw before, solving for, again, a Bayes-Nash equilibrium and seeing how that fares. All right, so how do we proceed? Well, we proceed like Myerson proceeded. We derive Myerson's result, again, the same characterization, but again, we have this annoying C in there. So it's not quite what we want because we're interested in payments, and we get a result that's kind of about this C-adjusted payments, which is not quite what we're looking for. But then, the key observation that we made right outside here in the hallway is this one on this slide. So we have this kind of annoying C here. We're interested in we're interested in maximizing the Qs. The Qs are our payments. This is the quality of our submissions. That's the thing that we want to maximize here. But we have this annoying C there, so we kind of have to invert that somehow. So looking here, you know, obviously Q is equal to the C inverse of C of Q. So that seems pretty clear. But what we noticed outside, this kind of minor thing but important, is that we can pop this C outside the expectation because of Jensen's inequality. And so since we can pop the C outside the expectation, what this is telling us, we want to maximize this quantity over here. Those are all the payments. And so what we can do instead is we can take as our payments C inverse of all this junk, and we can take those as our payments, and that's only going to get us more revenue than we had before. Okay, so we can do the inverse thing on the outside here, and that can only make us happier. So that was good news for us. All right, so we have a rough idea of what the payments are going to be in this auction we're designing. The next question then is, what is the allocation rule going to be? Because the payments, as we've been thinking about them here, remember they have this X hat in them. They're fully specified. Once you know the allocation rule, you know your payments. They're given by the payments identity. And so what we need to do then is we need to figure out an interesting allocation rule, or an appropriate allocation rule. It turns out to be interesting. So first thing we did was we thought about a bunch of examples, and here's something that we noticed. We set up a kind of crazy example, and in our crazy example, what we were able to show was that if you allocate to the highest bidder, so remember in first and second price auctions, you were always allocating to the highest bidder. If we allocated to the highest bidder in our example, we had a mechanism, our mechanism achieved the fourth root of n in revenue. On the other hand, if we allocated completely randomly, just uniform random, we were able to get square root of n revenue. Okay, so we're doing, you know, we have this rate of decay to 0 between the ratio between these two things, and what we're showing here is just allocating randomly in this setting is better than allocating to the best, to the highest bidder. Okay, and decaying to 0. All right, so that gave us some ideas to think about as to how we might want to allocate in this auction setup. And so what we came up with finally was that we are going to allocate uniformly at random to all competitors who are in the top quartile. Okay, so now in that example we were just doing it uniformly at random. You might think that you want to do just maybe the top half, and that's probably also a good choice. For us, the math worked out a little bit easier, just allocating to the top quartile, so that's how we did it. But in any case, the point is we're not allocating to just the best, just the highest bidder. We're allocating uniformly at random to anybody in the top quartile. And so now we have, you know, some theorems that say doing this is a Bayes-Nash equilibrium. That's good. And moreover, doing this is a constant approximation of the optimal. Again, I don't know the optimal. We had an upper bound on the optimal, constant approximation of that. And so that's also good. And so I think the takeaway message here is something that was characterized by a professor at Northwestern called Miner. He talked about something called the discouragement effect, which I think is maybe what we're seeing. So what he said was high-powered incentives in a relative performance world can actually destroy effort. In particular, since the less talented are less likely to win under competitive high-powered incentives, they may give up. And he dubbed this the discouragement effect. And in contrast, the most talented do increase their efforts when facing sharper incentives, so there's also the incentive effect. So it turns out that in many settings, the discouragement effect dominates the incentive effect, and that's basically what we're seeing here, that prescribing softer incentives is better. And the greatest overall effort can be elicited then by pushing more rewards towards the lower performers. Okay, so that was our conclusion as well, and something that he saw in his work simultaneously. Okay, so that kind of concludes my discussion of optimal contests and of mechanism design, and I want to change gears now. Well, actually, there's still a little more mechanism design, but I want to change gears and talk a little bit more about data and inference. All right, so maybe I'll pause for a sip of water and then continue. Okay. All right, so underlying that entire story was the assumption that we knew the distribution of values or the distribution of abilities of the participants in the mechanism. So this is not generally true. We can't generally assume this. But one thing that we do have a lot of these days are data. So here we're looking at a simulation of a first price auction where all we have are the data. We don't have the underlying distribution. So the question is, what can we do? Can we design an optimal auction from just the data? So in this simulation, we have 200 runs of a first price auction. We're drawing, so in the simulation, of course, we know the underlying values. So in the simulation, we're drawing from the values, but the conclusions we're going to make are assuming we don't have that distribution. So here's a bunch of samples from those of how these bids are showing up, and you see that the revenue matches the higher bid in each of the two columns, right? Because it's a first price auction. So I'm going to ask the question, from the data, can we find the optimal auction? So can we make that work? So here's a first attempt at that. So of course the optimal auction, remember I said this earlier, it uses some kind of reserve price. So to find the optimal auction, the question is, what reserve should we set? And so here's a couple of choices. Maybe we'll set 0.5, maybe we'll set 0.75. And here we are rerunning through our data with the 0.5 and 0.75 and figuring out what our revenue is. And what we find is, I don't know, for example, here at 0.75, we're getting 0 here. Why is that? Because neither of these agents have bid above 0.75. So we're running kind of a broken simulation here, right? We're sort of, what we're doing is we're just, by introducing this reserve price, we're just zeroing out a bunch of our entries, because any time that these bids don't turn out above the reserve, we end up with 0. So from this simulation as it is right now, it looks like introducing a reserve price is a bad thing to do. But that's, of course, because we're doing this wrong. This is a first price auction. Remember, in a first price auction, you shade your bids. Remember the housing example earlier, right? You don't bid your full value. So what we need to know in order to do this kind of optimization is we need to know what values were driving those bids. So we need to invert that bid function to back out the values that motivated that behavior. So if you do that, then you find that, in fact, by introducing reserve prices 0.5, 0.75, you can see that revenue is actually going up. So does that make sense? In the first cases, we were just throwing stuff away because we were just looking at the bids as they are. In this case, we first backed out the values. We figured out what values were motivating the behavior. Then we introduced a reserve price and recomputed the equilibrium. So these bids are now, these revenues are coming in under new bids that were using the values and using the reserve that we were testing in each of the columns. All right, so we can do this repeatedly, and we can see that, as you increase your reserve price, your revenue in equilibrium is going up for a while and then eventually going down. Okay, so this exercise is effective as long as you take your bid data, and from your bid data you back out your values so that you can then push them forward in the new equilibrium that you are considering. All right, so all of that conversation leads us to inverse reinforcement learning, which of course is about exactly this, about backing out values. So we've been working at Brown, a whole bunch of collaborators, as part of the Humanity Centers Robotic Initiative on some human-robot collaboration. And for this, we are using inverse reinforcement learning, meaning we are backing out values again to see what motivates, what drives certain behaviors. So many of you probably know this. We'll do it quickly. Inverse reinforcement learning is usually studied in the framework of Markov decision processes. And so a Markov decision process is a model where an agent is operating in a state, and the agent can then take some action. After taking that action, they will transition stochastically to some other state, and likewise will stochastically receive some rewards. And this process is repeating. So in an MDP, you're typically given the states, you're given the actions, you're given the transactions, you're given the rewards, you're given everything. Everything is fully specified, and your objective is to find an optimal policy, which means an optimal mapping from states to actions, what you should do at every state. There are lots of examples of MDPs. I'm sure you're familiar with many of them. I usually talk about the recycling robot in my classes. You know that one? He used to go around from office to office collecting the Coke cans and deciding if he should go and recycle his battery or go collect more Coke cans for more rewards. Well, I tried to, update myself a little bit. So I found another more up-to-date example here. This is the robot Bartender, who apparently is also run by an MDP. So this is not a robot Bartender, who's like a coffee machine that you kind of select at like a vodka on the rocks, and that kind of comes out from the machine in a coffee machine style. This is a robot who's actually trying to anticipate, oh, that patron over there would like to be served, and that one is willing to wait a little bit longer, and I should really get to this guy, and he has been served already, he hasn't, and so on. And so has all of this in his state, and is being controlled by an MDP in the background. All right, so I've, of course, mostly been interested in games, so we are thinking about this inverse reinforcement learning in a slightly more general context, which is in the context of Markov games. So a Markov game generalizes a Markov decision process. Again, you have a state, but now you have multiple agents. So your multiple agents are all taking actions simultaneously, and then they will transition to some other state, and they will all get rewards. So here are some examples of Markov games that we've thought about. So in these games, they're grid games, obviously. So in these games, we have yellow and blue agents. And the yellow and we're showing the initial states of the games here. So the yellow and blue agents in this first game are starting off on one another's goals. So the yellow agent has a yellow square as its goal. The blue agent has a blue square as its goal. So for example, in this hallway game, they're trying to get from, to cross each other in the hallway. They can't cross each other in the hallway. If they bump into each other, they just kind of keep bouncing back. All right, so they have to figure out some way to kind of get around one another to get to their respective goals. So this is kind of maybe a model for when you're walking down the street and you see somebody in front of you and you kind of don't know if you want to go this way or go that way, and you're kind of, back and forth on that. All right, and all of these games are like this. In all of the games, the way that they're set up, the blue agent is being blocked from his goal, the yellow agent is in his way, and likewise, the yellow agent wants to get his goal, but he's blocked by the blue agent. All right, so we've primarily done experiments with this first game, the hallway game. And interestingly, I went to a Women in Machine Learning workshop a year or two ago and ran into Joelle Pineau. And she's building a smart wheelchair. And her smart wheelchair, she said, has to solve exactly this problem. The wheelchair is kind of rolling down the hall, and a person's coming the other way. And it kind of has to figure out which way it wants to go to avoid the person who's approaching it. All right, and moreover, she's attempting to build these wheelchairs that are adapted to the user's needs. So again, to adapt something to the user's needs, you need to know something about their rewards, their values, like what is motivating their behavior. So maybe IRL is applicable there as well. All right, so how are we going to build a robot that is going to collaborate with a human? There are a couple of strategies, approaches we might take. So first thing we did here is on the hallway game, we ran a bunch of experiments on Mechanical Turk. And in these experiments, we just observed humans' behavior and ultimately kind of clustered it. This was done just manually. We sort of looked at the behaviors and decided whether people were looking like they're mostly competitive, just trying to get to their own goal, or whether they were sort of friendly and trustworthy and maybe waiting for the opponent to also get to their goal, or maybe they just give up and only want the opponent to get to their goal, all of these different types of behaviors. And so we looked at this actually with two different treatments. In the first treatment, the individual reasoning treatment, each of the players would get 100 points if they reached their goal. And so you see kind of a nice wide distribution of behaviors when you have this individual reasoning treatment. In the team treatment, we changed the payoff so that you could only get the 100 points if your opponent also got to their goal. Okay, and not surprisingly, you get a lot more cooperation when you are only going to get your points when your opponent also gets to the goal. So we were sort of able to manipulate humans by changing their rewards to make them friendlier. So we also did the same thing with Q learners. We also ran experiments just with the agents, and again, we manipulated reward sum. So what you're looking at here is you're looking at runs with a selfish and with a more fair agent, which is the one with the rewards that have been manipulated. And so this, the selfish agent just gets the 100 points when he hits the goal, but the fairer agent has this reward function where he has his own reward, that's RA for the agent, but then he gets a penalty if his reward is very different than his opponent's reward. Okay, so we kind of made things a little bit fairer by giving the agents penalties if they were not nice to their opponent. But the interesting thing here is that what we're reporting in this graph, obviously you see that the red lines are mostly higher than the blue, but what we're reporting here is not kind of the team rewards, which of course are going to be higher, but you even do better for yourself. So we're just reporting the one agent's reward. And by using this reward function, which is encouraging the agents to be friendlier, we're making everybody individually better off. So they're better off in this setting by being more cooperative. All right. So, but we don't want to hard code the rewards. We don't want to manipulate the system by, giving humans the exact encouragement to have well, maybe we do want to do that. But okay. But anyway, for the agents, preferable would be to extract the rewards, to extract the preferences that are representative of what, extract preferences that are representative of the behaviors that we're observing. And so this is exactly what inverse reinforcement learning does. So in inverse reinforcement learning, you again have an MDP, but the rewards are not specified. Instead, you're given data, and your objective is to back out the rewards from the data that you observe. So for example, one way of solving IRL problems is with maximum likelihood IRL. So there the goal is exactly what I just said. You want to find the rewards. So rewards here are represented by this theta. You want to find the rewards that maximize the likelihood of the data. So this is typically done by assuming that all the sample behaviors are optimal. So we have a bunch of trajectories, and we assume that whoever was doing the demonstrations was perfect and did everything exactly right, and then we can back out rewards that would be consistent with those behaviors. Now, there have been some exceptions to this, and we will be another exception to this. So we have kind of this more generalized IRL model, where what we're assuming is that trajectories can be labeled as either positive or negative, or maybe even things in between. And so our graphical model looks like this, where we have these labels coming out, and that's part of the data that will be given to the agent. But in addition, we assume that there's some latent variable there, which is on-state action pairs. And that latent variable is saying whether one particular action taken out of state is any good or not. So the idea being that if you have a whole bunch of positive labels on your state action pairs, then you'll end up with a positive label on the whole trajectory. And if you have a bunch of negatives, you would end up with negative. And I'll also note that you could have a positive label on an entire trajectory, but just identify one particular action at one particular state as not being very good. Okay, and that was actually sort of what we were going for when we were developing this model. So one of the examples that I have in mind for this, it's not a hallway kind of example, it's just a travel example. But before Michael Littman moved to Brown, he was at Rutgers in New Jersey. So I would sometimes have to ask Google Maps, how do I get from Providence to New Jersey? And so Google Maps would give me the route, and I would, on the whole, want to label this route as positive because it was getting me from my goal to my destination, from my source to my destination. So I'm achieving my goal. But the problem was it would very often take me on this road that's called the Cross Bronx Expressway. I don't know if any of you have ever been on the Cross Bronx Expressway, but you don't want to be on the Cross Bronx Expressway. The Cross Bronx Expressway is probably a 5-mile road north of Manhattan, but it's like you've got like these tall walls on each side of you, and you've got trucks, and there are fumes, and you can't breathe, and nothing moves. You sit there for an hour. It's just terrible. So I have to have the ability to tell Google Maps or to tell my IRL that I have to X out the action of taking the Cross Bronx Expressway. Get me from Providence to New Jersey, please, to Rutgers, but don't take me on that particular route. All right, so this is our model, and so we're going to do maximum likelihood IRL again, kind of assuming that we have these latent labels that are motivating the labels overall that we have on our trajectories. Okay. So I don't think I have time to go into the details of how we did this, but there's really not that much that's novel here. We're using EM. We're using gradient ascent. We're using importance sampling. We're using all of the standard techniques to solve this model. All right, so here's just one quick example of the behavior we observe. So here we have one sample trajectory through a grid where the goal is this purple. And we've labeled blue is a puddle, so you don't want to be in a puddle. So we've labeled that with this red to indicate negative. And this red square, well, we're kind of neutral about it. We don't really care that much one way or another. So that's the label that we've given. So if you look here on the right, you will see the output of our algorithm on that example. And so here, blue means that you've reached your goal. So you can see also on these arrows are indicating the optimal policy. So we have the reward function as well. The reward function you can't read. We've never been able to read it, sorry. The output is not big enough, but it's those tiny numbers. But what you can see is you can see the policy. Okay, so you can see here in this goal that we're just kind of deciding to move into the walls. We're happy to be in our goal. That's a good place to be. But the most interesting part of this, and I'm sorry, and red is bad and purple is kind of neutral. The most interesting thing about this is that here in the bottom left, from that one trajectory, the algorithm has figured out that it wants to go, around this puddle. This is kind of a neutral place to be. Let's move around it. And so as a control, we have just the one trajectory for just a standard ML-IRL. And here we find that it's a little bit confused. It's maybe thinking that that's a goal. It's just I don't know what it's thinking. But it's not quite clear that it needs to get out of there and get around. But it doesn't think it's too expensive as far as it understands to get all the way to the goal with that route. Now, this is kind of a disadvantaged thing, right? Because we gave a little bit of extra information to the one algorithm, and the other one still had just the one trajectory. Maybe we need to give the other one 3 trajectories or 5 trajectories, and it would learn just as well. All right. Running out of time, I want to say that we are bringing this into the domain of back to our original domain of the hallway game and other games. So running and extracting these rewards while they play the game. We're able to back out the rewards and push them forward to see what the next equilibrium is going to be. So this is like the initial game and then the final. What we haven't done is we have not brought this into the realm of humans and robots. What we really want to do is have one of these players be a human and the other player be a robot. And then if the human prefers one equilibrium or the other, it should be able to tell the robot, no, I don't like the equilibrium you're playing. That move you made in that particular state was not a move that I want you to make. And then it can, the robot should replan based on that information and do whichever equilibrium the human actually was heading towards. That's our objective. All right, I'm going to go quickly. All right, so first of all, I have to apologize. I told you, anyway, no deep learning. But I did say in my abstract something very different than what I actually talked about. So I advertised that we talk about wireless spectrum auctions and ad exchanges, neither of which I talked about. I am happy to talk to anyone during the day today about either of these things. I've certainly done some work in them. I mean, the main thing to say about these application domains is, and it kind of ties back into what I was talking about at the beginning about your expression of preferences. So all the optimal auction theory that I presented was all in a very special case of a single dimensional model. We had that one V. It was talent or it was your value. You had the one V, and when you have that one dimension, you can solve these problems, or at least Myerson solved the linear utility problem optimally. In these other problems, wireless spectrum and ad exchanges, these are multi-dimensional problems, kind of like the school preferences I was complaining about. I couldn't express my preferences exactly as I wanted to. So these are where your preferences have multiple dimensions. And in that case, these auction problems are not well understood at all. And so, what we're doing here, this kind of work, is very heuristic based. We're developing bidding strategies to try to find equilibria. I mean, and sometimes the equilibria don't even exist, right? So we're sort of maybe relaxing our notions of equilibria so we can find some existence, and then running lots of heuristics to try to even discover these equilibria. So these problems are much harder because they're in a much higher dimensional space. One thing I wanted to mention about the combinatorial auctions is that there's been some new work based on a combinatorial auction in 2014 that was run in Canada, where they released all their bidding data. So there was a paper just now at AMAS in 2017 where somebody has created a kind of value generator. So they've taken the bidding data and they've somehow generalized it so that if you ping their value generator, it's like a black box giving you bids from the distribution that they have generated. And so the point is that I now have bidding data, so we could try to think about backing out the values. I mean, this is much harder, again, because we're in this multi-dimensional space. But if we want to think about the optimal auction problem in for this harder domain, we have some bidding data that we can work from, which to me is very exciting to potentially try to figure out how we can optimize in this space. OK, so really, I'm out of time, but happy to talk about ad exchanges as well with anyone. So, quick summary. I talked a bit about at least approximately optimal mechanism design in the case of contests. And we had this maybe somewhat counterintuitive result that you don't just want to allocate to the top bidders. We also talked a bit about inverse reinforcement learning. And we have a new and general model, which we hope to potentially deploy on our robots. The main thing about that is that you have to back out the values that are motivating the behavior. If you back out the values that are motivating the behavior, then you can change the environment and you can predict how the agent is going to act in the new environment. That's really what we want to be able to do. And so this inference process from data is very important and driving a lot of the work that I'm doing. OK, thank you all for being here.
Thanks, Amy. We have time for a few questions. There will be people walking around the room with microphones. If you just raise your hand, we will bring a microphone to you. I can't see the number one.
Thank you for the fantastic talk. I really enjoyed this. My name is Katja Hoffmann. I'm a researcher at Microsoft Research in Cambridge. And I'm particularly interested in your work on human-robot collaboration. I'm wondering how you think about the incentive structure that could or should eventually govern those kinds of interactions. Do you assume, or should we assume, that an AI collaborator or robot should mimic or kind of align with the human's reward structure and utility, or should there be a different, should it have its own incentive that may or may not be aligned with the human operator?
That's a very good question. So for what I've been talking about, I was sort of assuming that it would just be, what the human was going to be able to direct the robot towards something that was satisfying the human. But I can certainly imagine a world where that is not the case, where we generalize and we somehow give the robots their own incentives and maybe allow those incentives to evolve as well. So I think maybe that's a little bit dangerous, but maybe that will, I don't have an example off the top of my head, but I could imagine that that might actually somehow lead to even better results for the humans. I mean, that's kind of along the lines of what I was saying before about the experiment with the Q learners, right? We kind of changed those rewards and that, so that you were going to be more fair, but that was better for you as well. So maybe we can give the robots some incentives, and by letting them, work kind of on their own behalf, they might even benefit us simultaneously. I guess in the end, what I'm saying is I'm very human-centric. I want it to, in the end, be good for us, but be good for us in a way along the lines of David Karger's question yesterday, in a kind of complementary way, kind of complementing the goals that we're trying to achieve. Yeah.
Number three.
Hi, thank you for the talk. You talked about the problem of allocating just to the top leaders in the sense of discouraging some of the participants. Can you talk about the applications of this result in education, for example?
In education?
Yeah, when you don't want to discourage students which might be struggling.
I haven't thought about that, but that seems to be a very good question. You have a comment on that? Yeah?
Give him a mic. Yeah, we'll bring a mic down right here.
I've thought about it mostly in the context of my NSF proposals.
Number two.
I have the same question, but I don't have a comment, although I do want to probe your theorem a bit more. I found it interesting that your reward function chooses this 1/4 as the top to distribute the rewards. And then the approximation to the optimal bound is very nice. It's 1/16, if I remember correctly. But if I parameterize your reward function choice of 1/4, do I get possibly closer or farther away?
Yes.
Do you have results to say that 1/4 is actually the optimal?
No, for sure not. Yeah, so I think we can do better. We were a little bit lazy, as I said, in the math, right? I mentioned maybe half and then a quarter. So a quarter worked, and we were happy we got our constant approximation, and we kind of quit. But I think that there's potentially, you can do better. But it doesn't answer the question about what we're going to do in the realm of education. So I don't think I know offhand. Do you have suggestions? I'd be interested. I haven't thought about it. But your point is that maybe some students are not the best students, and so if we're not giving them A's, then they might just be discouraged and quit. So we should somehow give motivation that they could maybe get an A, even if they, yeah. Okay, so I can imagine all sorts of crazy grading schemes where that could come out. So I think that's an interesting thing to think about. I have not particularly thought about it, but happy to talk about it, brainstorm about ideas. Anything to do to motivate the students to study harder, absolutely. Yeah.
Okay, we have time for one more question. Any last questions before we take off? Okay, well, join me in thanking Amy for her talk.